Chapter 4. Measurement of matter. Dear students, we have learned that compounds are formed by chemical combination of elements. We have also learned that molecules of a compound are formed by joining atoms of different elements, and the composition of a substance changes during a chemical change. Now let's do one activity. Take a solution of calcium chloride in a conical flask and a solution of sodium sulfate in a test tube. Tie a thread to the test tube and insert it in the conical flask. Seal the conical flask with an airtight rubber cork and weigh using a balance. The weight is X. Now tilt the conical flask so that the solution in the test tube gets poured in the conical flask. Now weigh the conical flask again. Oh, what do you find? The weight is same, X. So from these activities, we came to know that the mass of the original matter and the mass of the matter newly formed as a result of the chemical change are equal. This is law of conservation of matter. According to this law, in a chemical reaction, the total weight of the reactants is the same as the total weight of the products formed due to the chemical reactions. Now, law of constant proportion. The French scientist Proust stated the law of constant proportion as the proportion by weight of the constituent elements in the various samples of a compound is fixed. That is, the proportion by weight of hydrogen and oxygen in water is 1:8. This means that 9 grams water is formed by chemical combination of 1 gram hydrogen and 8 gram oxygen. Many compounds can be made by different methods, but the law of constant proportion is always true. Then, atom, size, mass and valency. We know that at the center of an atom is the nucleus and that there are moving electrons in the extranuclear part. The electrons are negatively charged elementary particles, while the elementary particles that make up the nucleus are positively charged protons and electrically neutral neutrons. The size of an atom is determined by its radius. The atomic radius of an isolated atom is the distance between the nucleus of an atom and its outermost orbit. The atomic radius is expressed in nanometers. The atomic size depends on the number of electron orbits in the atom. The greater the number of orbits, the larger the size. But if two atoms have the same outermost orbit, then the atom having the larger number of electrons in the outermost orbit is smaller than the one having fewer electrons in the same outermost orbit. For example, an atom of magnesium is smaller than an atom of sodium. Then the mass of an atom. The mass of an atom is concentrated in its nucleus and it is due to the protons P and neutrons N. The number P plus N in the atomic nucleus is the atomic mass number. And protons and neutrons are together called nucleons. An atom is very, very tiny. Then how do we determine its mass? It was not possible for scientists of the 19th century to measure atomic mass accurately. Therefore, the concept of relative mass of an atom was put forth. A reference atom was required for expressing the relative mass of an atom. The hydrogen atom, being the lightest, was initially chosen as the reference atom. The relative mass of a hydrogen atom, which has only one proton in its nucleus, was accepted as 1. Therefore, the magnitude of the relative atomic masses of various atoms became equal to their atomic mass number P plus N. For example, the mass of one nitrogen atom is 14 times that of a hydrogen atom. Therefore, the relative mass of a nitrogen atom is 14. This is how the relative atomic masses of various elements were determined. On this scale, the relative atomic masses of many elements came out to be fractional. Therefore, in the course of time, different atoms were chosen as reference atoms. Finally, the carbon atom was selected as the reference atom. In this scale, the relative mass of a carbon atom was accepted as 12. The relative atomic mass of one hydrogen atom compared to the carbon atom becomes 12 multiplied by 1 upon 12, that is 1. The mass of one proton and of one neutron on the scale of relative atomic masses is approximately 1. Today, we have highly accurate methods for measuring the mass of an atom directly. Hence, instead of relative mass, unified mass has now been accepted as the unit of atomic mass. It is called Dalton and the symbol is U. 1 U is equal to 1.66053904 into 10 raised to minus 27 kg. Then chemical symbols of elements. Dalton used certain signs to represent elements. For example, this sign for hydrogen. Today, we use the symbols determined by IUPAC, that is International Union of Pure and Applied Chemistry. These are official names and symbols and are used all over the world. The current method of choosing chemical symbols is based on the method invented by Berzelius. According to this method, the symbol of an element is either the first letter or the first and the second specific letter in its name. Of the two letters, the first is a capital letter and the second is small. For example, sodium. One more example, C carbon, Ca calcium, Co cobalt. Then molecules of elements and compounds. Atoms of some elements such as helium, neon have independent existence. It means these elements are in a monoatomic molecular state. Sometimes two or more atoms of an element combine to form molecules of that element. Such elements are in a polyatomic molecular state. For example, oxygen is a diatomic molecular state, O2. When atoms of different elements combine with each other, the molecules of compounds are formed. Then, molecular mass and the concept of mole. Molecular mass. The molecular mass of a substance is the sum of the atomic masses of all the atoms in a single molecule of that substance. It is also expressed in the unit Dalton. For example, H2O molecule is having the constituent elements hydrogen and oxygen. The atomic mass of hydrogen is 1 U and that of oxygen 16 U. The number of atoms in the molecule are 2 hydrogen atoms and 1 oxygen atom. Therefore, atomic mass into number of atoms is 1 into 2 and 16 into 1, that is 2 plus 16, that is 18. So, the molecular mass of water is equal to 18 U. When elements and compounds take part in chemical reactions, it is their atoms and molecules that react with each other. However, while carrying out a chemical reaction, it is convenient to measure out quantities that can be handled instead of counting the number of atoms and molecules. The concept of mole is useful for this purpose. 1 mole of a compound is the mass of that substance in grams equal in magnitude to its molecular mass. The SI unit is mole. So, number of moles of a substance N is equal to mass of substance in grams upon molecular mass of substance. Avogadro's number. The number of molecules in 1 mole of any substance is constant. The scientist Avogadro did pioneering work in this context. Therefore, this number is called Avogadro's number and is denoted by the symbol Na. The value of Avogadro's number is 6.022 into 10 raised to 23. A mole of any substance stands for 6.022 into 10 raised to 23 molecules. Just as a dozen has 12 items, a century has 100. A mole means 6.022 into 10 raised to 23. Then valency. The capacity of an element to combine is called its valency. The valency of an element is indicated by a specific number, and it is the number of chemical bonds formed by one atom of that element with other atoms. For example, sodium atom is having electronic configuration 281. It gives away one electron and a cation of sodium is formed. Hence, the valency of sodium is 1. The electron configuration of chlorine atom is 287. It takes up one electron and forms an anion of chlorine, that is chloride, and thus the valency of chlorine is 1. After the give and take of electrons is over, the electronic configuration of both the resulting ions has a complete octet. Due to the attraction between the unit but opposite charges on the two ions, one chemical bond is formed between sodium ion and chloride ion, and the compound sodium chloride is formed. Thus, the valency of both the elements sodium and chlorine is 1. And therefore, valency means the number of electrons that an atom of an element gives away or takes up while forming an ionic bond. Positively charged ions are called cations, while negatively charged ions are called anions. The electrons present in the outermost orbit of an atom are called valence electrons. The number of electrons that are given away or taken up is always a whole number, and therefore valency is always a whole number. Then variable valency. Under different conditions, the atoms of some elements give away or take up different number of electrons. In such cases, those elements exhibit more than one valency, and this property is called variable valency. For example, iron Fe exhibits the variable valencies 2 and 3, and therefore iron forms two compounds with chlorine, FeCl2, that is ferrous chloride, and FeCl3, that is ferric chloride. Compounds with ionic bonds have two constituents. These are a cation, that is positively charged ion, and anion, that is negatively charged ion. They take part independently in chemical reactions and therefore called radicals. The cationic radicals are also called as basic radicals, and the anionic radicals as acidic radicals. Generally, basic radicals are formed by removal of electrons from the atoms of metals such as sodium ion, but there are some exceptions such as ammonium ion. Similarly, the acidic radicals are formed by adding electrons to the atoms of non-metals, for example chloride ion, but there are some exceptions like MnO4 ion. Monoatomic radicals such as sodium or chloride ions are simple radicals, or when a radical is a group of atoms carrying charge, it is composite radical, for example SO4 ion, NH4 ion. The magnitude of charge on any radical is its valency. Then chemical formulae of compounds, recapitulation. The name of an ionic compound has two words. The first word is the name of the cation, and the second is the name of the anion. For example, while writing the formula of a compound such as sodium chloride, the symbol of the cation is written on the left, and adjoined to it on the right is the symbol of the anion. The charges are not shown, though the number of the ions is written as a subscript on the right of the symbol of the ion. This number is obtained easily by the method of cross multiplication of the valencies. The steps are: to write the symbols of the radicals. Step 2, to write the valency below the respective radical. Step 3, to cross multiply as shown by the arrows the number of the radicals. Step 4, to write down the chemical formula of the compound.